Hi, welcome to section 10.2, which is on polygons and tessellations. We're going to start with talking about angles in a triangle, and then we'll move to all different types of polygons. So when we think about a triangle, any triangle really, I'll draw a picture of one on the paper, but it could be any shape. So any type of triangle. And we think about what the angles add up to. You may have heard that the angles in a triangle add up to 180. And if you haven't heard that, that's okay too. But why do they add up to 180? So I just want to go over a couple of different ways that we could show, just really easily show kids how to prove this. So there's all kinds of more complicated theorems, but we're just looking for simple here. So one way to do this is to get a triangle and cut out a triangle using a piece of paper. And you could do this at home if you want to test it out. So use a straight edge, draw a triangle. It could have any type of triangle. The sides do not have to be the same. And what you do is then take scissors and you cut the angles off of the triangle. So cut them off. And then what you do is you take the angles and you piece them together, and they might be, slightly different sizes, and that's okay, like in terms of lengths. But the angles, so let me just get a different color here so it's really clear. So if we think about the actual angles right here, what will happen is when you cut them out, they will come together and form a line. And so it just shows that these add up to 180 degrees because 180 degrees makes a line. And really the magic in this is to have many kids, like your whole entire classroom of children, do this all at the same time because they're going to make different types of triangles. So to see it be done with different types of triangles, different sizes, different types of angles, and see that they all come together to make 180 is pretty eye-opening. And then the other thing you can do, so that's paper tearing. So you can show this with paper tearing. So you can show this with paper tearing or cutting. So you cut off the angles of the triangle. The other thing you can do is just use folding. So you create a triangle with a sheet of paper. So create this triangle just like the one that we have here. Draw it over real quick. So we have our triangle. And if you want to, you can use different colors to highlight the angles. And then what you do is you're going to fold those angles either in or you can fold them down. So this side is going to come down. So basically what it'll look like is it'll look like this with that edge folded down. And then you're going to fold the sides in left and right. So then this side will come in like this, and they'll both be folded in so that the angles come together at the center. And just by folding, you can see that those angles come together to make a straight line. So you can either tear them or fold them. And the best way to do this is to get out a triangle and try it on your own at home. It doesn't take long and you'll be convinced. So let's talk about the angles in any polygon. So let's just revisit. The definition of a polygon is a simple closed figure made of line segments, so no curves. And we can scroll down here. I've got some pictures of some common polygons that, so we've got triangles, squares, pentagons, hexagons, heptagons. Those are just a couple. And so every polygon has three types of angles: central, vertex, and an exterior. And it's important that you know how to locate these. So central angle is formed when you create a center and you connect the center to the vertices. So the vertices are the points where the line segments meet on the polygon. And you take your center and you connect your center to each one of those vertices. And what it does is it creates some central angles. So the central angle, this right here is an example of one central angle. And in this figure, this is a six-sided polygon, so this is a hexagon. There are six central angles, so 1, 2, 3, 4, 5, 6. So there are six central angles in a polygon, or not a polygon, a hexagon. So in this case, we have a hexagon. So for our example, and we have six central angles. And then let's talk about vertex angles. So vertex angle, and I'm going to erase the central so we can see the vertex really clearly. So we identified the vertices before. So here's a vertex that's singular, vertices, there's 6 of them. And the vertex angles are the angles that are at each one of those vertices. So there are 6 vertex angles in a hexagon. And then the exterior angles are much less clear to see. What you have to do with to find the exterior angles is you locate a vertex and then you go in one direction, either counterclockwise or clockwise, you choose, and then you just, I'm going to go counterclockwise, so I'm going to head to the right. And then you just draw a line following the side and then you keep going. And the angle that's formed between that side extension and the next side is the exterior angle. And then you keep going. So you go to the next vertex and you do it again. And there's an exterior angle. You go to the next vertex and you extend the side and there's your next one. And then you go to the next vertex. And so you keep going till it looks like one of those straw hats. And so we end up forming 6 exterior angles. So with any polygon, you're going to have the same number of central angles as you do sides, and the same number of vertex angles and the same number of exterior angles as you do sides. And so there's some properties with all of those angles, and we'll talk about those today. So to draw a regular polygon, this is a fun thing to do with kids, especially if you're just looking for an activity to use a protractor. If you happen to have a protractor at home, you could do this and try this on your own. The instructions are right here. But a regular polygon is a polygon with congruent angles. All the angles are the same measure, and then congruent sides. So these are examples of regular polygons and we can even label them, like the regular pentagon, for example. All of these sides are the exact same length. And it's possible to have a pentagon. There are other pentagons we could draw where there wouldn't be regular. So anything that's 5-sided. So 1, 2, 3, 4, 5. So this is a pentagon. Imagine those lines are straight. And it's just not regular. So think of like a stop sign would be a regular octagon, for example. So to draw a regular polygon, if you want to try that, you can. Basically, you have to draw a line segment. So you use a ruler. Whoops, I don't know why that decided to connect. So we're going to draw a point and you draw a line segment. And you measure off the degrees in one vertex angle. So you're going to find the degree measures, and we'll talk about those down below. So for example, in a hexagon, the vertex angle of a hexagon is 120 degrees. So what you do is you take your protractor. So a protractor is one of those tools that looks like this, and it's got a bunch of measurements on the side. It goes from 0 to 180 degrees, and you measure off 120. So you measure off what 120 degrees would look like. And then you're going to make sure, so mark off 2 sides of equal length. You're going to measure that first line segment. Say that first line segment was 3 centimeters, and you're going to take your ruler at that 120 degree angle, and then you're going to measure 3 centimeters. So you have a side that doesn't look super accurate. Try to make that a little better. And you're going to try to make that other line segment that's also 3 centimeters. And then you basically continue going around in a circle and measuring 120 degrees with your 3 centimeter side length, 120 degrees with your 3 centimeter side length. And when you come all the way around, you'll end up creating a regular hexagon. So with a protractor and ruler, it's not too difficult to do. So there's an activity called the angle sum activity that I like to do with kids, and if we were in class with you, I would have you do this activity. And basically what it does is I pass out a worksheet where I have a bunch of polygons drawn on the worksheet. And there's a 3-sided polygon and 4 and 5 and 6 all the way up to 9-sided polygons. And these are not regular polygons. These are just, polygons with the specific number of sides. So the sides are not all the same length, but they have the number of sides listed here. And then what I have students do is I have them measure with a protractor all of the angles inside of each polygon. And so they measure the angles inside of each polygon, and then we write them down. And here is what we find. So we find that the total, the angle sum inside of a triangle, any triangle, is 180 degrees. We find the angle sum inside of a four-sided figure. So that could be a rectangle, it could be a square, it could be a trapezoid. We see that the angle sum there is 360 degrees. We see an angle sum in a five-sided figure. We add up those angles, and I mean this angle, and this angle, and this angle, and this angle, and this angle. We add those up and we get 540. We take a six-sided figure, so 1, 2, 3, 4, 5, 6, and maybe I'll make that a little bit, whoops, 1, 2, 3, 4, 5. I gotta swing this one out. 6. So there's a six-sided figure, definitely not regular, but it's got six sides, and so we measure all of those angle measures, and we find that the sum of those is 720. So these are not perfect looking polygons, but they all add up to 720. No matter what they look like, as long as they have six sides, the angle measures add to 720. All the seven-sided figures end up adding to 900. All of the eight-sided figures add up to 1080 degrees. All the nine-sided figures add up to 1260 degrees. And then what we do is we go through each figure and we identify the number of triangles that can be formed in each type of figure. So let's go ahead and draw these and identify the number of triangles by connecting one vertex to the remaining vertices, and I'll show you what I mean by that in a second. So a triangle is made up of one triangle, pretty obvious there. A four-sided figure, so let's say 1, 2, 3, 4, and it doesn't matter what type of figure as long as it has four sides. So this I just happened to draw a trapezoid. If we make triangles by taking one vertex and connecting to the other vertices, we end up forming two triangles. If you make a five-sided figure, so 1, 2, 3, 4, 5, and I am just making this up on the fly, so it should hopefully show you that it's any five-sided figure. It does not have to be a perfectly regular one. If we pick a vertex and we connect with the other vertices, watch what happens. We end up getting three triangles. Okay, let's do it again. Let's do it with a six-sided figure. So if we take 1, 2, 3, 4, whoops, not enough. Try that again. 1, 2, 3, 4, 5, 6. Take a vertex and we connect it with all of the other vertices. We end up getting 1, 2, 3, 4 triangles. Do you see a pattern? And it keeps going. So a seven-sided figure ends up having 5 triangles. An eight-sided figure has 6 triangles. A nine-sided figure has 7 triangles. Do you notice a relationship between the number of sides and the number of triangles? So number of sides, number of triangles. There's always 2 less number of triangles than there are sides. Well, the nice thing about a triangle is we know through paper folding and tearing, we did some simple demonstrations that show that the angle sum of a triangle is 180 degrees. So we know that the angle sum inside of a triangle, three-sided figure, is 180. Well, let's look at how we get 360. Think about it for a minute. If we know there are 2 triangles and each triangle is 180 degrees, 2 times 180 is 360. 3 times 180, since there's 3 triangles, is 540. 4 times 180 is 720. 5 times 180 is 900. So in all of these cases, if we want to know the total angle sum of all those vertex angles without getting a protractor and measuring all of them, all we have to do is take the number of sides and take the number of sides, subtract 2, to find the number of triangles, and then multiply by 180, and that gives us the angle sum. And so the formula for angle sum, I'm basically working through this so you can see where this formula comes from, and you're not just like, well, where the heck did that come from? So the number of triangles, this column, is always n minus 2. So if n is the number of sides, there are 2 less triangles than number of sides. Every triangle is worth 180, so if we want the angle sum, all we have to do is take 180 degrees times n minus 2. So this is the number of triangles, and then we multiply by 180 because there's 180 degrees in each triangle. Okay, so the formula is 180 times n minus 2 for the angle sum of any polygon. I mean, you saw the ones I drew. They were not perfect. Now, if we want to find the measure of a vertex angle, one vertex angle in a regular polygon, so let's talk about that. So now we're talking about those perfectly looking polygons. So let's take a pentagon, for example. So I'm going to try to draw as best I can. I'm going to try to draw a regular pentagon. 4, 5. So let's pretend that I did a decent job here. Let's pretend that all of these sides are equal. And so if I know that the angle sum of a pentagon is 540 degrees, and I know since it's regular that all of these angles are the exact same measure, all I have to do is take 540 and divide by 5, and that'll give me the angle measure of one vertex angle. So we know this is 108, and this is 108, and 108, and 108, and 108. This only works if it's regular, because if it's not regular, these are all different measures that add up to 540. So let's keep going. So if I want to know the individual, so the measure of one angle in an equilateral triangle, I just take 180 and divide it by 3 to get 60. For this one, I take 3 for a 4-sided figure, which is a rectangle, or in this case, it'd be a square. 360 divided by 4, and you get 90. So I'm going to take 720 for a regular hexagon and divide by 6, since there's 6 sides, and I get 120. So above, when I did that hexagon demonstration and wrote 120, that's how you get the 120. For a heptagon, which is a 7-sided figure, you're going to take the 900 and divide it by the 7, and you end up getting 128.57. So sometimes we get measurements that are not whole numbers. That's totally okay. And then 1080 divided by 8 sides, we get 135 degrees each. And then last but not least, if we do 1260 divided by 9, a 9-sided regular polygon is going to have vertex angle measures of 140 degrees each. So in general, what we're going to do is we're going to take the sum and divide by the number of sides. Whoops. And we want to actually convert this using the equations here. So I'll wait till my computer is done acting up here. There we go. So number of sides. So sum, we said, was 180 times n minus 2, and number of sides is n. So this is the formula. You got a couple of important formulas here. So this one and this one you're going to need. So this first one again is the angle sum of any polygon, and this second formula here is the measure of one vertex angle in a regular polygon, because we're dividing by the number of sides. Okay, so now let's do some examples. So this would be a great place to pause the video and try these on your own using those formulas and see how you do. So for the first one, example 1, find the missing angle measures. So I know I'm just going to write a little 90 here. I know that's 90, so I'm going to call this X. I don't know what that is. The first thing you want to do when you find missing angle measures is you want to know the sum. So this is a 4-sided figure. So I'm going to do 180 times 4 minus 2, and I end up getting 360 degrees for my angle sum. So now I know that all of these need to add up to this sum. So I'm going to say X plus 110 plus 55 plus 90 equals 360. And so I combined the numbers. So X plus 255 equals 360. I subtract the 255 from both sides, and I end up getting x equals 105 degrees. And then before you move on to the next one, just take your calculator and add all those up and make sure they add to 360. Just go backwards. So same thing with the next one. So now this is also a four-sided figure. If you had a problem where it was a five-sided figure, make sure that you do the formula for sum and take that into account. They're not all going to add to 360. It depends how many sides the figure has. So in this case, it's the same type of figure with the same number of sides, 4. So I'm going to add all of these up and set them equal to 360. Now in this case, I've got a couple variables in different locations. So anywhere I have an x, those are all like terms, I'm going to combine those. So I've got 1x, 2x, 3x, and a half. I'm going to write 3.5x. I think that'll be a little bit simpler. And then minus 30 plus 5 is minus 25 equals 360. Then I'm going to add 25 to both sides. That 25 goes away. I get 3.5x is equal to 385. And then I divide both sides by 3.5. And I end up getting 110 for x. Example 2, the measure of a vertex angle, so that's important, of a regular polygon is 120 degrees. How many sides does it have? Now you could certainly look at the table, or you might just remember, oh yeah, it's a hexagon, 6 sides, because we just talked about that. Let's go through this problem though from the very beginning, so that way we can see how you'd use the formula in case you were given a degree measure that you weren't familiar with or that wasn't on your table. So as soon as I see vertex angle of a regular polygon, I think of the formula. So I'm going to write down the formula, which is 180 times n minus 2 divided by n. That's the vertex, that's for one vertex angle in a regular polygon. I'm going to set that equal to 120 degrees because that's what this angle in this regular polygon is. And then I'm going to solve for n. You can do this in a couple of different ways. You can multiply both sides by n, or you could put this over 1 and you could cross multiply. I'm going to do that way. So I get 180 times n minus 2 equals 120 n. And then I'm going to multiply that 180 in, so 180n minus 360 equals 120n. I get the n's together, okay, and so I'm left with negative 360 equals negative 60n. Divide both sides by negative 60, and I end up getting 6, so 6 sides. And again, the nice thing about this process is that this will work for any different type of angle, or any different angle measure, rather, and that way you can use it if you're not familiar with the angle measure given. So let's talk about some central angle formulas and some properties. So let's look at this, this figure. So what do the central angles add up to? So we had some sums for the vertex, but let's talk about the central angles. So here we have an octagon that has 8 sides. So it has 8 central angles. So if it's a regular octagon, it means all of those central angles are going to be the same. So each angle would measure, so if these all come together to make a circle, which central angles always do, then they're going to be 360 divided by 8, or 45 degrees each, assuming the octagon is regular. So they're always going to end up adding to 360, but the fact that they're all the same, that has to do with the fact that they're regular. So all of these angle measures, these are all 45 degrees, because 45 times 8 is 360. So in general, the sum of the central angle measures in any polygon, even polygons that are not perfect, like if you think about, you know, if I were to just draw one here, if I were to find the central angles here, you can just eyeball this and see that these are not the same. Like this angle here is not the same as this one, but they do all make a circle and they all add up to 360. So the sum is always 360. But the measure of one central angle, if you have a regular polygon, because it's the only way you'd be able to find this out, is 360 divided by n. And remember, n is just the number of sides. Okay, So the next part here, exterior angle, I've got a little proof here on the right, but I'm actually going to explain this in a different way because I think there's a clear way to do it. But you can see here that with the exterior angle, so this is the example of, this is one exterior angle. You could keep going and keep drawing and extending these lines and see all of the exterior angles. But you can see here that the vertex angle and the exterior angle, those make a line and they add to 180 degrees. This is an important property to keep in mind. It can sometimes help you solve problems. So this just means the measure of an exterior angle plus the measure of the vertex angle equals 180. So what I like to do to prove this, rather than go through a geometric proof, is I like drawing polygons, and so the activity that I described earlier, what I would have students do is I would have them draw out the exterior angles for all of the polygons on their paper, and then I would have them put them together, and what would happen is you'd see all of the exterior angles come together, and they might all not be the same, but they would all come together to make a circle. And so exterior angles actually add to 360 as well, just like a central angle. So if we scroll down here, we can see in the box we've got exterior angle formula. The sum of exterior angles in any polygon is always 360. And if you want to know the measure of one exterior angle in a regular polygon, then you just divide that by n, which is the number of sides. So exterior angles and central angles in regular polygons will always be the exact same because they always add up to a 360. So let's do an example where we bring all of this together. So for a regular 16gon, so you can always refer to a polygon as the sides and then dash gon, like 8gon, even though we call it an octagon, you could still refer to it as an 8gon. So it's a 16-sided polygon. Let's find the sum of all vertex angles. So the sum formula is 180 times n minus 2. That's the sum formula. So I just plug in the number of sides, 16, and that'll give me my sum of 2,520 degrees. If I want to know the measure of one vertex angle and it's regular, then I can use the formula 180 times n minus 2 divided by n. I just divide by the number of sides. Now I already did 180 times n minus 2. I already found that that was 2,520, and then all I have to do is divide that by 16 and I get 157.5 because 157.5 times 16 is the angle sum, 2520. The measure of central and exterior angles, C and D, are going to be the exact same because it's always 360 divided by n for both. It's the same exact formula. So it's 360 divided by 16, which is 22.5 degrees. And so the same thing will be true for that one. So the last part of this section, we're going to kind of change gears here and talk about tessellations. So tessellations are basically, you can look at it as just a compilation of polygons when you put them together. So, and it's called a polygonal region. So a tile floor, for instance, in a bathroom is often a tessellation because usually a tile floor is, usually it's square tiles, sometimes it can be hexagon tiles, but you have a bunch of tiles that are put together without any gaps, and that's a tessellation. There's a famous mathematician. His name was M.C. Escher. He's a graphic artist who's also a mathematician, and I'll show you he's famous for creating tessellations, and these are some of his tessellations. Now you'll notice his tessellations, they aren't all polygons. I mean, a fish is definitely not a polygon. It has lots of curves, but it's a loosely defined definition of a tessellation. So he takes one shape and he repeats it and puts them together, or he might even take a couple different shapes and put them together. Sometimes it's not always the same shape. So just some examples of tessellations there. So the key here is figuring out, you know, which shapes are going to tessellate. Will every shape tessellate? How can you figure out what shapes are going to tessellate? And the way that you figure out what shapes are going to tessellate is you look at their angles. If you were to put three triangles together, for example, like an equilateral triangle, if you were to put an equilateral triangle together, it would look like this. So pretend these triangles are all the same size. Not so much, but pretend they are. If they're all equilateral triangles, all of these vertex angles are going to be 60. And what's nice about 60 times 6? Well, 60 times 6 is 360. They come together perfectly to make a circle without any gaps. Think about a square. So if you take a square together, we see this all the time, or rectangles with like a brick outside. These are all 90-degree angles. And what happens when you take 90-degree angles and put 4 of them together? You end up getting 360 and they end up meeting. So that works. So we know that an equilateral triangle tessellates. So we say yes. We know because the interior angles add to 360. Will any triangle tessellate? So the problem with any triangle is that, or actually, let's ask if all triangles will tessellate. And the answer is no, not all triangles, because some triangles are going to have different angle measures that won't be 360. So if you take, for instance, a triangle where maybe one of the vertex angle measures is 50 degrees. Well, when you add up 50 over and over and over again, you can get close to 360. So 50, I know 50 times 7 is 350. So if I put 7 of these together, 1, 2, 3, 4, 5, 6, 7, we end up fitting them, but then there's this gap with some space left over. It's 10 degrees extra because I'm at 350 and not quite enough room to stick another triangle. So not all triangles are going to tessellate, but an equilateral triangle will. A square will tessellate, yes. A rectangle will, because those angles are 90 degrees. Any quadrilateral, so think about like this, this parallelogram here. Now this one you can see that will tessellate because we can make these angles meet together at the middle. But will any? I'm not so sure. I mean, think of a trapezoid like this. You could find a trapezoid where one of the angle measures is 50, and just like the triangle above, if you tried to stick that 50-degree angle together all the way around a circle, it's not going to make 360. So not all. But the interior angles on a square and a rectangle have to add to, or they do add to 360. So not all, but the rectangle and the square add to 360, and the equilateral triangle can add to 360. So there are 3 regular tessellations. So the square and the triangle we just talked about. The hexagon also works. Let's talk about a hexagon. The vertex angle of a hexagon we already talked about is 120. Well, if you take 3 120-degree angles, 120 times 3 is 360. So again, that works. Anytime those vertex angles divide 360, you will have a tessellation. So each of their vertex angles divide 360. This is the important part. That's what makes it tessellate. All others do not. So a couple other things about tessellations, and then we'll be finished. So there's we can name tessellations, and I'm going to do that down here, and then I'll come back to the semi-regular part. So we name tessellations by picking a vertex, any vertex, so any point in the tessellation. So imagine like your tile floor, like in your bathroom. You can look at the corner of any tile and imagine that as a vertex. And then ask yourself, what are the shapes of the tiles that all come together to meet at that point? And you're going to list out the number of sides of the shape that's coming together to meet at that point. So for example, this is a 3-sided shape here because it's a triangle, and another triangle, 3-sided shape, and a 3-sided shape, and a 3-sided shape, and a 3-sided shape, and a 3-sided shape. So the way you would name this would be like right here. It'd be 3, 3, 3, 3, it'd be 6 3s, because this basically represents 6 3-sided figures coming together. Sometimes you have tile floors where they're not all the same shape. So take this point, for instance. You've got a 4-sided shape, and then a 1, 2, 3, 4, 5, 6, 7, 8, an 8-sided shape, and then an 8-sided shape all coming together to meet at that point. So you could say 8, 8, 4. You could say 8, 4, 8. You could say 4, 8, 8. It doesn't matter which one you start with, you just go around in the circle and you name all the shapes. Now we're going to swing back here and talk about semi-regular tessellations. So a semi-regular tessellation is a combination of regular polygons where, and this is important, I didn't put this on the notes, so make sure to write this in. There must be the same arrangement at every vertex. So that means you pick a vertex, like I picked this one, and I look at the arrangement. So I've got a 6-sided figure, 6-sided 4. Okay, so that's a 6, 6, 4. So then I come to another one. This is 6, 6, 4. If I come to this one here, now you got to kind of use your imagination here because we didn't continue the tile pattern, but looks like there'd be a square there. So this would be a 6, 4, 6. So the 2 6-sided and then a 4. So it looks like this one is semi-regular. Let me pull up an example from our textbook. And we can see these are 2 examples here. So, and I can't write on this with my pen since it's not a Word document, but you can see, let's look right here at this vertex where the hand is. So at this vertex right here, it looks like I've got a square. I've got a 1, 2, 3, 4, 5, 6, a hexagon. So square, hexagon, square, triangle. So you have a 4, 6, 4, 3. 4, 6, 4, 3. And then if I come up here, I've got a 3, 3, 3, 4, 4. So there's no hexagon touching this vertex. So this would not be a semi-regular tessellation. And just visually, you can see that there's this hexagon pattern running in the middle, but then it doesn't run throughout here. Not every single vertex is touching, has a hexagon meeting at it. So this would not be semi-regular. Now this one down here, you have to use your imagination because it's not continued. But if you look right here, this has the makings of another, it looks like it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like it's a decagon. And it looks like here that this has another making of a decagon right here in this opening. So if I look at this vertex right here, and I'm just picking one, it could be anyone. Looks like I've got a decagon, 10-sided figure, 4-sided figure, 6-sided figure. So 10, 4, 6. And then if I look at this vertex, it looks like I've got a 6, a 4, and a 10. Or right here, there's a 10. Imagine there's a 10 here, a 6, and a 4. So this one to me seems like it's semi-regular because at every vertex you're going to have the same arrangement of polygons. So I hope that helps. That's it for section 10.2. If you have any questions, just let me know.